Hi all, welcome to Go Classes. In this lecture, we will continue the GATE PYQs and TIFR PYQs based on the concepts vertex cover matching independent set click in the graph theory. So this is part 2. In the previous part, we have solved some TIFR and some GATE previous year questions. The link you can find in the description in the pinned comment. Okay, this is GATE PYQs and TIFR PYQs part 2. Okay. So find the part 1 in this playlist on the Go Classes YouTube channel. Basically, on YouTube, you can search Go Classes Discrete Mathematics, and this playlist will be there. Discrete Mathematics, GATE PYQs, Compact Course, Practice Questions, Revision playlist. In this playlist, you can find the part 1 also. Okay. Or you can find the part 1 in the description, also in the pinned comment. You can check it out. Let's solve GATE IT 2008 question. What is the size of smallest MIS? MIS means maximal independent set. So, what is the size of smallest maximal independent set of a chain of 9 nodes? This is a simple question. First of all, what is chain of 9 nodes? The name itself is telling you it is simply a chain of 9 nodes, means it is basically a path graph on 9 vertices. Okay, chain means it's like a chain, it's like this. Okay, so you can see it's a chain of 9 nodes. That means this is a path graph on 9 vertices. It's like a1, a2, a3, and so on, a9. Okay, very simple. Now in this path graph of 9 vertices, we need to find the size of smallest maximal independent set. Remember, we want maximal independent set that is smallest. Okay, what is maximal independent set? What is the definition of maximal independent set? This is an independent set in which we cannot add a new item, we cannot add a new element without violating, without losing this independent set property. Okay, very simple. Maximal simply means it cannot be made bigger. Okay, this maximal, this word, what it means? It means that we cannot make it bigger, cannot make bigger by adding a new item, cannot make bigger by adding a new item, by adding a new item in it. Okay, very simple. Remember, maximal may or may not be largest, maximal may or may not be maximum. Maximal, this means we cannot make it bigger by adding a new item in it. So maximal independent set means this is an independent set in which we cannot add a new item without losing the property of independent set. Okay, so what is maximal independent set? This is an independent set which is not proper subset of another independent set. Okay, so I can say maximal independent set. This simply means this is an independent set which is which is not which is not a proper subset, which is not a proper subset of another another independent set. Okay, is this clear? Very simple. So maximal independent set definition means that this is an independent set which is not a proper subset of another independent set. Or I can say that maximal independent set means this is an independent set in which we cannot add a new item without losing the independent set property. Or I can say that maximal independent set, it is an independent set that cannot be made bigger by adding a new item in it. I hope you understood. Now we need maximal independent set which is smallest. Remember, different maximal independent sets can have different sizes. All the maximum independent set have the same size. So please understand the difference between maximal and maximum. In our lectures, we have already seen this difference. Okay, you can find the link in the description in the pinned comment. I will not cover it here, but you can see there is a difference between maximal and maximum. Maximum means largest. So maximum independent set, that means this is a largest, this is the largest, or I can say this is the largest independent set. And remember, maximum may or may not be unique. Maximum independent set may or may not be unique. You can have one or more than one largest independent set, but all the maximum independent set have the same size. But remember, different maximal independent sets may have different sizes, and we need to find the smallest maximal independent set. Among all the maximal independent set, we need to find what is the size of smallest maximal independent set. I hope you understood. So let's see. Let's solve this question. So what we have chain of 9 nodes. That means we have a path graph on 9 vertices: a1, a2, a3, a4, a5, a6, a7, a8, a9. Okay, this is what we have. So we have a chain of 9 nodes, or I can say we have a path graph on 9 vertices. Now in this, let's find some maximal independent sets. Okay, let's find the maximum. First, let me find the maximum independent set in it. Okay, maximum means largest independent set in it. Okay, so for largest independent set, what you can do, you can start with this vertex a1. Okay, you can take a1. Then of course you cannot take a2 because we are finding independent set. So in the independent set, we have vertices which are pairwise non-adjacent. You can see a1, a2, they are adjacent. So with a1 I cannot take a2. Then I can take a3. Okay, so we can take a3. Then I cannot take a4 because a3, a4 are adjacent. And independent set means set of vertices which are pairwise non-adjacent. So after a3 I can take a5. After a5 I can take a7. After a7 I can take a9. This is maximal independent set. Actually, for this particular graph, for this p9, there is a unique maximum independent set. This is actually unique. Okay, for this graph. But remember, for a general graph or maybe for a different graph, remember the maximum independent set, this may or may not be unique. Okay, so you can see here for this graph p9, the maximum independent set, that means largest independent set, that is actually unique here. Okay, so this is the only maximum independent set for path graph on 9 vertices. Okay, what is the size of maximum independent set for this graph p9? The size of maximum independent set, that is 5. And remember, the size of maximum independent set, that is called independence number, that is denoted by alpha. Okay, so alpha of p9, that is 5. What is this alpha? This is independence number. And what is independence number? This is the size of maximum independent set. Okay, this is the size of maximum independent set. Very simple. I hope you understood. Remember, every maximum is also maximal. So this is maximal also. Okay, this you already know, that every maximum entity is maximal too. Okay, it is maximal too, but not the converse, or I can say not vice versa. Not vice versa means maximal may or may not be maximum, but every maximum entity is maximal also. So remember here, this maximum independent set, this is maximal also. Okay, now let's find some more maximal independent set. So now our focus will be on maximal independent set. Okay, now already we have found one maximal independent set because every maximum independent set is also maximal. So I can say that a1, a3, a5, a7, a9, this was maximal. This is maximum also, this is maximal also. So yes, this is a maximal independent set. Okay, now do we have another maximal independent set? Let's see if we have. What I can do, I can take a1. Okay, I can take a1, then I cannot take a2. Then I can take a3. Let me take a3, no problem. Okay, then I cannot take a4. Now what, let me do one thing, that let me take a6, because remember, if I take a6, I have already taken a1, I have taken a3. If I take a6 instead of a5, if I take a6, now you can notice that I cannot take a2 because a1, a2 are adjacent. I cannot take a4 because a4, a3 are adjacent. I cannot take a5 because a5, a6 are adjacent. Okay, now what I can do, Now I can take A8. Now on your screen, you can see if I take these four vertices, if I take, then that will be maximal independent set, because now I cannot add a new item without losing the property of independent set. If I add any new item, then I will lose the property of independent set. Okay, so you can see we got maximal independent set of size 4 we have got. Okay, so this is what I'm saying, that A1, A3, A6, then A8 I can take. Okay, so this is another maximal independent set. Okay, now you might be thinking, is there any other smaller maximal independent set, because the question is asking the smallest maximal independent set. So you can see in this, for this graph P9, is there a smaller maximal independent set? Can we create a maximal independent set of size 3? That is the question. Okay, so let me check. Let me do one thing. To find smallest maximal independent set, let me ignore this A1, because I can take A2. If I take A2, I cannot take A1, I cannot take A3. Okay, do you agree? Let me start with A2, because I want smallest maximal independent set. I want a independent set in which I cannot add a new item without losing the property of independent set. Okay, and I want smallest number of elements in this maximal independent set. So let me start with A2. If I start with A2, then I cannot take A1, I cannot take A3. Now, then I can take A4, but let me ignore A4, let me take A5. Notice one thing, if I take A5, now I cannot take A4, I cannot take A6, I cannot take A3, I cannot take A1. Now, after this A5, I cannot take A6. Let me ignore this A7, let me take A8. Now you can see if I take A8, then I cannot take A9, because A8 and 9 they are adjacent. A7, 8 they are adjacent. I cannot take A6 because 5, 6 are adjacent. 4, 5 are adjacent, so I cannot take A4. 2, 3 are adjacent, I cannot take A3. And 1, 2 are adjacent, so I cannot take A1. So did you notice? Now these three vertices, if I take, then this is a maximal independent set, because I cannot add a new item without losing the property of independent set. So very simple, remember, we got this A2, A5, A8. This is another maximal independent set we got. Another maximal independent set. And this is the smallest, because can you create a maximal independent set of size 2? Is it possible that I can create a maximal independent set of size 2? Remember, A1, A2, at least one of them you need to take. It's necessary. Okay, very simple point I am telling you, that is there any size 2 maximal independent set? This is my question. Is there any size 2 maximal independent set for P9? Okay, this is the question. So now you notice one thing, that these two vertices A1, A2, at least one of them I need to take, because if you don't take any of them, okay, let's assume you are taking some vertices from here and you don't take any of them, A1, A2, you are not taking any of them, then this is not maximal independent set, because I can add A1. Do you agree? See, from here you are taking some vertices and you are making independent set. Now I can say that it is not maximal, because I can take A1. Okay, yes or no? A1 is not adjacent to all these vertices. So I can take A1, I can add this new item in the independent set. So I can say that from here, if you create independent set, then that is not maximal. So it's necessary that from these two vertices, at least one of them I need to take. Out of these two, at least one of them, okay, at least one of them I need to take here. At least one of them I need to take. Okay. Similarly, you can see A8, A9. Here also, at least one of them I need to take. Okay, yes or no? You can see here also, at least one of them I need to take. The same logic. Okay. Now, so already what we have, if I take at least one of them, A1, A2, and if I take at least one of them, A8, A9, then already I got size 2 independent set. Now what about the remaining vertices? You can see that from the remaining vertices, at least one vertex I need to take, because if I don't take any of these remaining vertices, if I don't take any of them, then I will not get independence, I will not get maximal independent set, because I can add A5. Okay, from here if I take one element, from here if I take one element, then I will not get maximal independent set. I will get independent set, but I will not get maximal independent set, because I can add this new item. Yes or no? This new item A5, this is not adjacent to A1, A2, A8, A9, so I can add this A5. So definitely this independent set that I am getting from A1, A2, A8, A9, this independent set, this is not maximal, because I can make it bigger by adding this A5. Okay, so very simple point that at least 3 size I need. Okay, is this clear? Very simple point. So I can say, is there any size to maximal independent set? The answer is no. Okay, the answer is no. So finally, I can say that this size 3 independent set that you created, this A2, A5, A8, this is maximal independent set, and this is smallest. This is smallest maximal independent set. Okay, I hope you understood this. So for P9, what is the size of smallest maximal independent set? That is 3. Okay, yes or no? So here the size is 3. So the answer will be, what is the size of smallest maximal independent set? The answer will be 3. Okay, very simple. I hope you understood. Remember one more thing, that these are not the only maximal independent set. You can create more independent set also. More maximal independent set also you can create. Can you give me some more? How many maximal independent sets are there? Can you tell me? For example, this is the question that I am asking. Take it as a variation. Let me ask you a question, that how many maximal independent sets are there? This is the question. Question is, how many, total how many maximal independent sets are there? Maximal independent sets are there for P9. Okay, this is the question. Total how many maximal independent sets are there for P9? Because I can create some more maximal independent sets. Okay, I can create, like, let me do one thing. Let me start with A1. After starting with A1, I can take A4. Okay, then I can take A6. Then I can take A9. This will be a maximal independent set. You can check. Okay, this is also maximal independent set. I can create some more maximal independent set. Let me take A1. Then let me take A3. Then let me take A6, and then let me take A8. This is another maximal independent set. Okay, so like this, there are and many more, and many more I can create. Okay, so my question is, how many maximal independent sets are there for P9? Will you do manual calculation? Will you calculate manually? Like, will you create all of them and will you calculate manually? Is that a smart method, that you are calculating manually all these maximal independent sets? The answer is no, that is not a smart method. So there must be some other method. Do you agree with me? My question is very simple. This is variation of GATE IT 2008 question that we have just solved. Okay, you can see this is GATE IT 2008 question number 4. For this, we have seen the answer is option C, but there is a variation that I am asking. The variation is, how many maximal independent sets are there in a path graph, or I can say in a chain on n vertices and nodes. So definitely you will not calculate manually. If you calculate manually, that is not a smart method. It will consume a lot of time. So there must be some smart method. What is that smart method? So let me tell you that smart method. And this is a note that I want to give to you. Okay, this is very important note. In this lecture, in this session, we are going to solve many questions based on this note. Okay, so understand this, that whenever there is a question, to count the number of matchings, or to count the number of independent sets, or to count the number of vertex cover, or to count the number of edge cover, to count the number of click, then always use recursive method. Okay, so let me tell you, this is a note that any question related to any question, any question related to, or I can say when we are counting, to count, to count number of, to count the number of matchings, to count the number of matchings, or to count the number of independent set, or to count the number of vertex covers, or to count the number of edge covers, or to count the number of clicks. Okay, so to count the number of these concepts in a graph, to count the number of these concepts in a graph, in a graph. Okay, so basically I can say note in a graph, in a graph G, to count the number of these concepts, what is the method? What you should do? Think recursively. Think recursively. We will do a lot of practice of this in this lecture. Think recursively. Okay, think recursively. Or I can say that count recursively. Basically, I can say that count recursively. Okay, so the counting you should do recursively. I hope you understood this. Now, you might be thinking how to do the counting recursively, how to write the recurrence relation, how to think recursively. So we will do a lot of practice in this session. A lot of questions we are going to solve, the gate PYQs, TIFR PYQs, and some variations from my side. But the point is, by the end of this lecture, you will become expert in thinking recursively to count the number of these concepts in a graph. Some graph will be given to you, maybe complete graph, maybe path graph, maybe cycle graph, maybe something else. Okay, and to count the number of these concepts, to count the number of matchings, to count the number of independent sets, to count the number of vertex covers, and so on, you always just think recursively, count recursively. Okay, so let's do a lot of practice of it. Let's solve this question. How many maximal independent sets are there in a path graph on n vertices? So how to think recursively here? So the solution, let me tell you, the solution is think recursively. Think, or I can say count recursively. So how to count recursively? Let me tell you. You have path graph Pn on n vertices. Okay, we have path graph on n vertices. For example, vertex, you can take like vertex 1, vertex 2, vertex 3, 4, 5, and so on, and so on, n. Okay, so very simple. This is the path graph on n vertices. Now, what are the base cases? See, whenever you are thinking recursively, then there must be some base cases. Okay, what are the base cases? For example, if you have path graph on n vertices, means if you have path graph on one vertex, if you have just path graph on one vertex like a1, then what will be the number of maximal independent sets? What that will be? Let's assume that, let's assume m, or maybe let's assume s. What is Sn? This is the number of, what is Sn? This is the number of maximal independent sets. This is the number of maximal independent sets in Pn. Okay, what is Sn? Please understand that Pn is a graph. Pn is the path graph. And in this path graph, total how many maximal independent sets are there? That we are denoting by Sn. So Sn is the number of maximal independent sets in Pn. Okay, so you tell me, in P1, what will be S1? S1 means the number of maximal independent sets in P1. So S1 will be what? That will be 1. Okay, because there is only one maximal independent set, and that is basically this A1. Yes or no? Okay, in this graph, there is only one maximal independent set, and that is this A1. Okay, what about P2? What about path graph on two vertices A1, A2? Now, here you tell me what will be S2, means the number of maximal independent sets in P2. So that will be 2. Okay, because you can take A1. If I take this A1, then this is maximal independent set. Or I can take A2. This is also maximal independent set. What about P3? P3 means path graph on three vertices A1, A2, A3. Here, what will be S3? S3 means total number of maximal independent sets in P3. So tell me, in this P3, how many maximal independent sets are there? Notice, if I take A1, I cannot take A2, then I must take A3 because I want maximal independent set. So I can take A1, A3, that is maximal independent set. Yes or no, I can take A1, A3. Or what I can do, I can take A2, that's it. If I take A2, then that is also maximal independent set. That's it. So S3 will be 2. Okay, is this clear? Very simple. So these are the base cases. You can see S1 means the number of maximal independent set in path graph on one vertex, then that will be 1. S2, that is 2. S3 is 2. So you can see for path graph on one vertex, two vertex, three vertex, we can easily find the number of maximal independent sets. Now, what about Pn? In Pn, in path graph on n vertices, I want to count what will be the number of maximal independent sets, means Sn I want to find. Okay, so you just think recursively. Let's see what this Sn will be. Notice, in the maximal independent set, either I will take this one or I will not take this one. Do you agree with me? Just focus on this one here. Okay, focus here. Just focus here. Then you can see what is the total number of maximal independent set in this path graph on n vertices. This is the path graph on n vertices. So the total number of maximal independent set, that is Sn. Now notice, in the maximal independent set, either I will take this one or I will not take this one. If I take this one, means this vertex 1 taken in maximal independent set. Okay, if I take this one, means this one is taken in the maximal independent set, then in that case, this is already taken, right? Okay, this is already taken. So definitely I cannot take this 2. Yes or no? If I take this one in the maximal independent set, then definitely I cannot take this 2 because 1, 2 are adjacent. I want independent set. Independent set is set of vertices which are pairwise non-adjacent. So you can see that if I take this one in the maximal independent set, then I cannot take this 2. Now notice, after taking this one, I just need to make a maximal independent set here. Yes or no? Here I need to make maximal independent set. Here I need to make maximal independent set. Already I have taken this one. This one I have already taken in the maximal independent set. So definitely 2 I cannot take. Now from this remaining graph, I need to find a maximal independent set. Do you agree with me? Okay, so I can say that if you take this one, then you cannot take 2. Now you just need to count how many maximal independent sets you can create from this remaining graph. And what is this remaining graph? This remaining graph is your Pn minus 2. This is a path graph on n minus 2 vertices. So in this path graph on n minus 2 vertices, you need to count how many maximal independent sets you can create. Okay, so what will be the number of maximal independent sets in this path graph on n minus 2 vertices? That will be Sn minus 2. Because what is Sn? This is the number of maximal independent set in a path graph on n vertices. And now you are finding the total number of maximal independent set in this path graph on n minus 2 vertices. So that will be Sn minus 2. Do you agree with me? Okay, so this is the situation where this vertex 1 is taken in the maximal independent set. So you cannot take 2. So now in the remaining graph, that is Pn minus 2, in this remaining graph, you need to make maximal independent set. So I can say that here you need to find the total number of maximal independent sets. That will be Sn minus 2. Now what is the another case? So you can see when this one is taken in the maximal independent set, then you got Sn minus 2. Now, or what can happen? Or one is not taken, in maximal independent set. One of these situations can happen. Either one will be taken in the maximal independent set, or one will not be taken in the maximal independent set. Either this or this, only the either this situation can happen or this situation can happen. Because of this, or you will add plus. Yes or no? Okay, plus. Now let's see what I should write here. When one is not taken in the maximal independent set, this one I have not taken. Tell me, if I don't take this one, then is it necessary that I must take two in the maximal independent set? If I don't take this one, is it necessary that I must take this two? Is it necessary? Yes, it is necessary, because you are not taking one. If you don't take two, and then if you make some independent set, that will not be maximal, because this one is not adjacent to any of these vertices. So you can add this one. Do you agree with me? Here, if I make an independent set, then that will not be maximal, because I can add one to it. Okay, yes or no? So remember, very simple. My purpose is to find maximal independent set. And if I don't take this one, then it is necessary that I must take two. It's necessary. If I don't take this one, then it will imply that two is taken. Okay. So now once two is taken, then definitely three I cannot take. Okay. So I cannot take 3 now. You can see in this remaining graph. What is this remaining graph? This is Pn minus 3. This is path graph on n minus 3 vertices. In this remaining graph, I need to find the maximal independent set. Okay, yes or no? So finally, I can say that if you don't take one in the maximal independent set, then definitely two I must take in the maximal independent set. If I take two, then three I cannot take. Now, from the remaining graph, that is Pn minus 3, I can make any maximal independent set. So I need to count the number of maximal independent set in this remaining graph Pn minus 3. The number of maximal independent set in this Pn minus 3, that will be equal to Sn minus 3. Okay, that's it. I hope you understood. So here you can see this is definitely implying. That's it. So this is the recurrence relation that we got. I hope you understood. Very simple. Remember, just focus on this vertex 1. And our purpose is to create maximal independent set. If I take this one in the maximal independent set, then I cannot take two. Then from the remaining graph, I need to make maximal independent set. So in the remaining graph, how many maximal independent set I can create? That will be Sn minus 2. And if I don't take this one in the maximal independent set, then I must take two in the maximal independent set. And because of two, I cannot take three in the maximal independent set. So in the remaining graph, I need to make the maximal independent set. And how many maximal independent sets are there in this remaining graph Pn minus 3? That will be Sn minus 3. That's it. I hope you understood. Okay, so the recurrence relation that we got, that is equal to Sn minus 2 plus Sn minus 3. Okay, and this recurrence relation will work when, remember this recurrence relation, when it will work? This will work when n is greater than equal to 4. Okay, why? What is the reason? Because here you can see if n is equal to 3, if I put 3, then here I will get as 0. But remember, every graph must have at least one vertex. Okay, see, did you understand why I am putting that when n is greater than equal to 4? This recurrence relation will work when n is greater than equal to 4. Why? What is the reason? Why? Why? What is the reason? Because you can see if I put n equal to 3 here as 3, then that will be equal to s1 plus s0. But we don't have s0. Every graph should have at least one vertex. So we have path graph on one vertex, path graph on two vertex, path graph on three vertex. We don't have path graph on zero vertex. So that is the reason this recurrence relation will work for n greater than equal to 4. Is this clear to everyone? Let me know. this recurrence relation will not work when you put n equal to 3 or n equal to 2, because if I put n equal to 2, then s2 will be equal to s0 plus s minus 1, means you have path graph on minus 1 vertices. Of course that is not possible. You don't have path graph on 0 vertex, you don't have path graph on negative number of vertices. So we have path graph on 1 vertex, so I must put 4 here, then I will get s2 plus s1. Okay, I hope you understood this. So remember, in Pn, what is Sn? Sn is the number of maximal independent sets. Maximal independent sets in Pn. Okay. So this is Sn. Sn is the number of maximal independent sets in Pn. So what will be Sn? Sn will be equal to Sn minus 2 plus Sn minus 3, where when n is greater than equal to 4. And what are the base cases? Base conditions. Base conditions are S1 was 1, S2 was 2, S3 was 2. So now you can find what will be S4, S5, and so on, S9. So now let's find what will be S4, means the number of maximal independent set in path graph on 4 vertices. What will be S5? What will be S6? Finally, we need to find S9. So what that will be? Okay, so you can see here what will be S4. S4 will be S2 plus S1. S2 plus S1, that is basically 3. What will be S5? S5 will be S3 plus S2. S3, S3 plus S2, that will be 4. S6, that will be S4 plus S3. S4 plus S3, that will be 5. Then you can see what will be S7, what will be S8, and finally we need to find S9. So S7 will be S5 plus S4, that will be 7. Then what will be S8? That will be S6 plus S5. S6 plus S5, that is 9. And what will be S9? That will be S7 plus S6. S7 plus S6, that will be 12. Okay, so I hope you understood. The answer will be 12. So remember, in path graph on n vertices, path graph on 9 vertices have the total number of maximal independent set 12. Okay, I hope you understood. The same thing I've written here, you can see on the gate overflow website under this question, this gate PYQ that we have just now solved. Okay, so under that question, this answer I have written here, you can see I have written the general result for counting the number of maximal independent sets in Pn. This recurrence relation I have written with the base conditions, and you can see I9, that is the number of maximal independent set in P9. Okay, so that will be 12. I hope you understood. Now let's solve gate and TIFR questions PYQs on matching. Let me tell you that in the gate, in the TIFR exam, from the matching, these type of questions have been asked, like counting the number of matchings, counting number of perfect matchings, counting number of maximal matchings, counting number of maximum matchings, and questions based on relationship between matching and vertex cover. So these different type of questions have been asked in TIFR, also in the gate exam. Let's solve all of them. Remember one thing, that to count the number of matchings, to count the number of perfect matchings, to count the number of maximal matchings, to count the number of maximum matchings, for these type of questions, always think recursively. We are going to do a lot of practice. We are going to solve a lot of questions, the gate questions, the TIFR questions, and some variations from my side. But you will become expert of thinking recursively to count the number of matchings, to count the number of perfect matchings, to count the number of maximal matchings, to count the number of vertex cover, to count the number of independent set, to count the number of maximal independent set, and so on. Okay, all these different type of questions related to counting can be solved if you think recursively. Okay, already one question we have solved, already one question we have done, where we were thinking recursively to count the number of maximal independent sets in the path graph. Okay, so by the end of this lecture, a lot of questions we are going to do, so you will become expert. Okay, so let's see. You can see this is gate 2003 question, where they are asking the number of perfect matchings in the complete graph on 6 vertices. So here they are asking you to count the number of perfect matchings. In this gate 2026 question, they are asking you to count the number of matchings in a path graph on 8 vertices. So you can see this is latest question in gate 2026. They are asking to count the number of matchings in a path graph on 8 vertices. You can see this is TIFR 2022 question where they are asking to count the number of maximal matchings in a path graph. Also, this is TIFR 2022 question which is related to relationship between vertex cover and matching. Okay, so I hope you understood that these type of questions have been asked from matching in gate exam in the TIFR exam. Okay, so let's solve all these questions one by one. Let's solve TIFR 2022 question. This question is based on the relationship between matching and vertex cover. The question is saying we are given a graph G along with a matching M and a vertex cover C in such a way that the size of M is equal to the size of C. So remember, a matching is given to you, a vertex cover is given to you, but remember this can be any matching. It is not saying that it is maximum matching or maximal matching. It is saying that it is some matching. It can be any matching. Also, this vertex cover can be any vertex cover. We are not saying that this is minimal vertex cover or minimum vertex cover. No, this can be any vertex cover. This can be any matching. So we have a graph in which there exists a matching M, there exists a vertex cover C such that they both have same size. Now consider the following statements. Three statements are given to you that M is definitely a maximum matching, C is definitely a minimum vertex cover in G. G is bipartite graph. Which of the following is true? Out of these three statements, which are true? Only based on this information that there is a graph G where there exists a matching M, there exists a vertex cover C such that their size is same. So if their size is same, then what can you say about this matching? Is it maximum? What can you say about this vertex cover? Is it minimum? And what can you say about this graph? Is it bipartite? This is what the question is asking. Now, to solve this question, you must understand the relationship between matching and vertex cover. This relationship we have already seen in our lectures with proof. We have seen the proof also. Here I will not discuss the proof, but I will tell you what is the relationship between matching and vertex cover. Okay, so let's quickly see the conclusion. The relationship between matching and vertex cover. This is the relationship that in any graph, the cardinality of any matching is less than or equal to the cardinality of any vertex cover. So remember, in any graph, whatever graph you take, the size of any matching is always less than equal to size of any vertex cover. So any matching, that means I can also take maximum matching. So I can say size of maximum matching is less than equal to any vertex cover size. Any vertex cover, so I can take minimum vertex cover also. So I can say that size of maximum matching is always less than equal to size of minimum vertex cover in any graph, whatever graph you take. Size of any matching is always less than equal to size of any vertex cover. So from here I can say that size of maximum matching is less than equal to size of minimum vertex cover. What is size of maximum matching? In any graph, the size of maximum matching, that is called matching number, that is denoted by mu. Okay, so that is less than equal to what is size of minimum vertex cover? In any graph, the size of minimum vertex cover, that is called vertex cover number, and that is denoted by beta. So this is the relationship between matching number and vertex cover number. I can say matching number is less than equal to vertex cover number in any graph. What is matching number? This is the size of maximum matching. What is vertex cover number? This is the size of minimum vertex cover. So size of maximum matching is always less than equal to size of minimum vertex cover. Mu is always less than equal to beta. This always happens. Okay, this relationship we need to use to solve this question. Okay, but actually let me tell you, in our lectures we have also seen that mu is less than equal to beta and beta is less than equal to 2 mu. Okay, this also we have seen. Okay, So with proof we have seen the proof of this this equation also, that mu is less than equal to beta. We have also seen the proof of beta is less than equal to 2 mu. Okay, I will not discuss the proof here. You can watch the lectures. The link you can find in the description, in the pinned comment, or on the YouTube you can search go classes discrete mathematics, and in the playlist you can find the lectures based on the lectures on matching, vertex cover, etc. Okay, there we have seen the proof. But this is the relationship between matching and vertex cover, and this relationship we need to use, that the matching number, I can say size of maximum matching is less than equal to the size of minimum vertex cover. Mu is less than equal to beta. Okay. So let's come to the question. You can see this is the theorem, or I can say this is the relationship between matching and vertex cover. That if M is matching and if S is vertex cover, then always remember the size of any matching is less than equal to the size of any vertex cover. So size of M is less than equal to size of S. Okay, very simple. You can see whatever matching you take, whatever vertex cover you take, always the size of matching will be less than equal to size of vertex cover, whatever graph you take. Okay. So let's solve this question. In this question they are saying that M is a matching. Okay, they are saying that M is any some matching. Okay, M is a matching. We don't know if it is maximum matching or not, we don't know, but M is a matching. And C is a vertex cover. C is a vertex cover. Okay, just tell me a very simple point. I don't know whether this M is maximum matching or not, but what do you think? The size of maximum matching and the size of M, how can you compare them? Tell me. See, M is some matching. It may be maximum, it may not be maximum. I don't know. I don't have that information. But you tell me the size of maximum matching. What is this mu? This is the size of maximum matching. This is the size of maximum matching. So, what can you say about the relationship between size of M and this mu? See, M is some matching. So, the size of M definitely will be less than equal to size of maximum matching. The name itself is saying the size of largest matching. M is some matching, but the largest matching size will be definitely greater than equal to M. Yes or no? Maximum means largest. So size of largest matching definitely will be greater than equal to M. Yes or no? What about this size of C and beta? What can you say about size of C and beta? What is beta? Beta is the size of smallest vertex cover. Size of minimum vertex cover. Minimum vertex cover. Okay, so you tell me this size of C and this beta, how can you compare them? Notice C is a vertex cover. I don't know whether this is minimum vertex cover or not, but the smallest vertex cover size, that will definitely be less than equal to the size of C. Yes or no? Because C is a vertex cover. It may be minimum, it may not be minimum. I don't have that information. But the smallest vertex cover definitely will have size less than equal to size of C. Common sense. Yes or no? So very simple. What we got that, okay, size of M is definitely less than equal to mu, and this beta is definitely less than equal to size of C. Okay, so far we are just using the common sense, nothing else. Okay, this is just a common sense, nothing else. This is not a concept, it's just simple common sense. Okay, now what relationship we know? We already know, that in every graph, what happens? We know that in every graph mu is less than equal to beta. Okay, this happens in every graph. And in the graph G, what is happening? In the graph G, size of M is equal to size of C. Okay, so you can see in graph G, in question, in graph G, in the TIFR question. So in the graph G, it is given that size of M is equal to size of C. Okay, this is given to you. And what we know, let me write here. What we know? We know that size of M is less than equal to mu. Beta is less than equal to size of C. Also, we know that mu is less than equal to beta. Okay, this is what we know. So, notice one thing, that mu is less than equal to beta and beta is less than equal to size of C and mu is greater than equal to size of M. Do you agree? From this information, this is what I can find. From here, this is what I can find. Correct? Because you can see mu is less than equal to beta. Mu is less than equal to beta. Beta is less than equal to size of C. And mu is greater than equal to size of M. So this single equation I can create. Also, this is given that size of M is equal to size of C. Let me call it K. Let me call it K. Then in this situation, this is also K. Size of M, this is also K. Size of C, this is also K. Then finally, what is mu? What is beta? What is mu? What is beta? That also will be K. Yes or no? You can see beta is less than equal to K, greater than equal to K. So definitely beta is K, mu is also K. So mu is also K, beta is also K. Okay, yes or no? So I can say that mu is actually equal to size of M. Okay, and you can see beta is actually equal to size of C. This is what we found. Is this clear? So finally I can say, that this is what we have found. So I can say that the size of M is equal to mu. And what is mu? This is the size of maximum matching. This is the size of maximum matching. Also, what we have found? We have found that size of C is equal to beta. And what is beta? This is the size of minimum vertex cover. Minimum vertex cover. Okay. So what you can say finally? Notice M is some matching. I don't know whether it is maximum or not. That information I don't have. But the point is, if M is some matching and the size of M is equal to size of maximum matching, then definitely M is maximum matching. Yes or no? Size of M is equal to size of maximum matching. So M is maximum matching. Yes. So we have found that M is maximum matching. Okay, so I can say that M is definitely a maximum matching. Okay, M is a maximum matching. So definitely I can say that M is a maximum matching. I can also definitely say that C is minimum vertex cover because C is a vertex cover. I don't know whether it is minimum or not. That information is not given to us, but we have found that size of C is equal to size of minimum vertex cover. C is a vertex cover and its size is equal to size of minimum vertex cover. So definitely C is a minimum vertex cover. So option, this statement 2, this is also true, that C is a minimum vertex cover. What about the statement 3? Can I say that G is a bipartite graph? This is false because remember from the König theorem. Do you recall the König theorem? In our lectures, we have seen this König theorem for bipartite graphs. Let me quickly do the recap of this König theorem. Notice one thing, in every graph, what happens? In every graph G, what happens? What is the relationship between matching number and vertex cover number? In every graph, the matching number is less than equal to beta, that is less than equal to 2 mu. Okay. So you can see the matching number mu is less than equal to the vertex cover number beta, that is less than equal to 2 mu. This happens in every graph, whatever graph you take. But remember, what is König's theorem? What did König proved? What did König proved? So König proved that in bipartite graph, if your graph is bipartite, in bipartite graphs, what happens? Mu is always equal to beta. Okay, means matching number is always equal to vertex cover number. This happens in bipartite graphs. This is Königs theorem, that if your graph is bipartite, then mu will be equal to beta. But remember, this is one way. Königs theorem is one way. Königs theorem is one way only. Is one way. What it means? It means that if your graph is bipartite, if your graph is bipartite, then it will imply that mu is equal to beta. But remember, if mu is equal to beta, then it does not imply that graph is bipartite. Okay, and here you can see in this TIFR question, mu is equal to beta. Yes or no? Because M is maximum matching, we have already found. C is minimum vertex cover, we have already found. And this is given that size of M is equal to size of C. So in this graph G, remember, so for graph G, it is given that for graph G, it is given that mu is equal to beta. Okay, this is given. But does it imply that G is bipartite? Does it imply that G is bipartite? No, it does not. It does not imply that G is bipartite. Remember, if graph is bipartite, then mu will be equal to beta. Yes, this implies. This is implied by Königs theorem. This is implied by Königs theorem. Okay, but remember, if mu is equal to beta in a graph, then it does not imply that graph is bipartite. I told you this when we were discussing Königs theorem in our lectures. You can see Königs theorem is one way. If your graph is bipartite, then definitely mu will be equal to beta, means matching number is equal to vertex cover number. But remember, in a graph, if mu is equal to beta, it does not imply that graph is bipartite. Okay, so Königs theorem is one way. This is what we have seen in our lectures. Now, let me give you a counterexample if you want. Consider this graph K4 minus 1As. This will work as a counterexample. So we have K4 minus 1As. We have A, B, C, D. We have all the edges except 1As. Okay, this 1As we don't have. So this is your K4 minus 1As. Now you can see in this graph, K4 minus 1As, in this graph, what is the matching number? What is mu? Mu means matching number, means size of largest matching. Here, if you notice, what is the largest matching that I can create? What is the maximum matching I can create? The maximum matching that I can create, I can take this AC, this edge I can take, this edge I can take. These are non-adjacent edges, so I can take AC, BD. This is the maximum matching I can create. Matching means set of edges which are pairwise non-adjacent. You can see AC, BD, these are non-adjacent. Okay, and in this graph, K4 minus 1 is in this graph, what is the minimum vertex cover you can create? Minimum vertex cover that you can create. So you can see this A comma B. Look at this A comma B. They will cover all the edges. Okay, yes or no? These two vertices A comma B, they are touching all the edges. So I can say vertex cover, minimum vertex cover, smallest vertex cover, that is A comma B. So the size of maximum matching, that is 2, and the size of minimum vertex cover, that is 2. So here you can see that mu is equal to beta. Okay, but remember, this graph K4 minus 1 is this graph, this is not bipartite. Why this is not bipartite? Because there is a triangle here. Yes or no? This contains a triangle. And you already know a graph is bipartite if and only if there is no odd length cycle. In this graph G, there is an odd length cycle. So this graph is actually not bipartite, but mu is equal to beta. So remember, mu is equal to beta does not imply that graph is bipartite. I hope you understood. This is the counterexample where mu is equal to beta, but the graph is not bipartite. I hope you understood. So remember, Königs theorem is one way. So if a graph has mu equal to beta, it does not imply that graph is bipartite, but if a graph is bipartite, then definitely mu equal to beta. Okay, so that's it. So finally I can say that this statement 3, that is not true, and answer will be only statement 1 and 2 are correct. So option D will be the answer for this TIFR question. I hope you understood the solution of this question. Did you notice, to solve this question, we are just using what we have already studied. We are using the relationship between matching and vertex cover. We have seen that in any graph, whatever graph you take, size of any matching is less than equal to size of any vertex cover. So size of maximum matching is less than equal to size of minimum vertex cover. So mu is less than equal to beta. And then we are solving this question. And also for this statement 3, we are using the König theorem. We have already seen that König theorem is one way. If the graph is bipartite, then mu equal to beta. But if a graph has mu equal to beta, then it does not mean it is bipartite. Okay, yes or no? So I hope you understood all these points. This is the complete analysis of this TIFR 2022 question. Let's solve TIFR 2022 question. G, V, E is a undirected simple graph. A subset M of edges is matching in G if distinct edges do not share a vertex. So the definition of matching is given to you, that is set of edges, or I can say subset of edges which are pairwise non-adjacent. A matching is maximal if no strict superset of M is a matching. So the definition of maximal matching is given to you. You already know a matching is maximal if it is not a proper subset of any other matching. Or I can say a matching is maximal if you cannot add a new edge without violating, without losing the property of matching. Okay, so very simple. The definition of maximal matching you already know, and that is given in the question. How many maximal matchings are there in the following graph? So this path graph is given to you on 6 vertices, and we need to find the number of maximal matchings. Now, how to solve this question? The one method one is we do it manually. Basically, this is path graph on 6 vertices. So we can count the number of maximal matchings because this is a small graph, only 6 vertices are there. So we can manually count the number of maximal matchings. We can create the maximal matchings and we can count the number of maximal matchings manually. This is method number 1. But tell me, is this smart method? If they give you, let's assume, path graph on 10 vertices, path graph on 20 vertices, then will you do manually? Will you count the number of maximal matchings manually? No. So there must be a smart method. Yes or no? If they are asking you this question that we need to count the number of maximal matchings in a path graph, then definitely there must be a smart method. And what is that smart method? That is think recursively. I told you in this lecture, in the beginning of this lecture, I told you that whenever there is a question related to counting matchings or counting independent set or counting vertex cover and so on, then always think recursively. Okay, so remember, to solve this question, there are two methods. Method number 1, that is manual. We will do it, don't worry. And the method number 2, that is smart method, that is we will generalize the result. We will find that whatever Pn is given to you, whatever path graph on n vertices are given to you, you can count the number of maximal matchings by thinking recursively. Okay, so that we will do. Now, first, let's solve this question manually. How most of the students will solve? So, most of the students, when they will see this question, then they will not think recursively, they will count manually. Okay, so this is how they will do. So basically, a P6 path graph on 6 vertices is given to you. 1, 2, 3, 4, 5, 6. Okay, this graph is given to you, and we need to count the number of maximal matchings. So count number of maximal matchings. Count number of maximal matchings in P6. Okay, so what is the method number 1? That is manual. That is manual, or I can say brute force. You can say manual method, or you can say brute force. Basically, nothing smart. You just do it manually, or I can say using brute force. So let's solve it using brute force. Let's solve it. in this manual method also, go systematic way. So first you consider this as 1 2. Okay, first you consider this as 1 2. So let's consider those maximal matchings which contain this age. Remember, what is a matching? This is set of pairwise non-adjacent edges. This is set of pairwise non-adjacent edges. Okay, we need to take set of edges which are pairwise non-adjacent. Okay, so let's consider those situations where this age 1 2 is taken. Okay, so let's take case number 1 where this age 1 2 taken. This age 1 2 taken in matching. In matching. Okay, so if 1 2 is already taken, then what are the possibilities? 1 2, this age you have already taken, then definitely I cannot take this 2 3. Yes or no? This age 2 3 I cannot take. Now what about this age 3 4? I can take it. Okay, if I take this 3 4, if I take this 3 4, then definitely I cannot take 4 5, and I must take this 5 6. Okay, this is one maximal matching. Another, you can see, if I take 1 2, then I cannot take 2 3. Now if I don't take 3 4, I must take this 4 5. See, if I don't take this, I cannot take 2 3. If I don't take 3 4, then I must take this 4 5, because if I don't take 4 5, then I could have taken this 3 4. Yes or no? If I don't take 4 5 also, then I will not get maximal matching, because I could have taken this as 3 4. So I must take 4 5. And after taking this 4 5, I cannot take 5 6. So you can see that in this case number 1, total two such matchings, two maximal matchings we got. In this case number 1, two maximal matchings we got. What about case number 2? Case number 2 means don't take this age. Okay, case number 2 means those maximal matchings where this age 1 2 not taken. Age 1 2 is not taken. If age 1 2 is not taken, then definitely I must take this 2 3, because if I don't take 2 3, then I will not get maximal matching, because I could have taken this 1 2. Yes or no? Remember, if I don't take 1 2 and I also don't take 2 3, then from here, whatever matching you create, that will not be maximal, because I could have added this age 1 2. So definitely, if I don't take this age 1 2, then I must take this age 2 3. After taking this 2 3, I cannot take this 3 4. Okay, yes or no? I cannot take 3 4. Now either I can take 4 5, or I can take 5 6. That's it. So in this case number 2, we got two such matchings, two maximal matchings we got. So finally I can say total how many maximal matchings we got? 2 in the case 2 and 2 in the case 1. So total 4 maximal matchings we got. So for this question the answer will be option D. So for this TIFR question, the answer is option D, 4, that we have already seen. But remember, we have solved this question manually, or I can say using brute force. That is not a good method, because in the gate exam they can ask you that maybe there are 10 vertices, maybe 12 vertices, 15 vertices. So they can give you path graph on n vertices, and they can ask you to count the number of maximal matchings in path graph on n vertices. So how to solve that question? You cannot do it manually, it will consume a lot of time, or maybe you will make some mistake. So there must be some smart method. What is that smart method? That is think recursively. So let me take a variation of this TIFR question. So this is the variation of TIFR 2022 question. How many maximal matchings are there in a path graph on n vertices? How to solve this question? I told you in this session at the beginning, I told you that to count the number of matchings, to count the number of maximal matchings, to count the number of independent sets, you always think recursively. That's it. Okay, so very simple. What you will do here, you will think recursively. So the solution is think recursively. Think, or I can say count recursively. So let's think recursively here. We have path graph on n vertices Pn. Path graph on n vertices 1, 2, 3, 4, and so on. Okay, this is the path graph on n vertices that is given to us, and we need to count the number of maximal matchings. This is what we need to count. We need to make maximal matching. Okay, so let's assume that Sn, let's assume Sn, this is the number of maximal matchings in Pn. Okay, so remember, I'm assuming that Sn denotes the total number of maximal matchings in Pn. So we need to count this Sn. We need to find this Sn. Manually, you can find S1 if your path graph on one vertex, if your path graph on two vertex, if your path graph on three vertex. Basically, S1, S2, S3, these you can find manually. These will be the base cases. But how to think recursively to find this Sn, that is total number of maximal matchings in Pn? So we need to find Sn. This is the point. So to find Sn, remember, just focus on this edge because we are thinking recursively. If you are thinking recursively, then just focus on this edge. Focus here. Focus on this edge 1, 2. What are the cases? In the maximal matching, this 1, 2, you take it or you don't take it. Only two cases are possible, that this edge 1, 2, this edge 1, 2 is taken in maximal matching. In maximal matching, or this edge 1, 2 is not taken in maximal matching, or this edge 1, 2 not taken in maximal matching. Only these two cases are possible. Do you agree with me? Either this edge you will take it in the maximal matching or you will not take it in the maximal matching. Only these two cases are there. Either this case is there or this case is there. Because of this or, you will use the symbol plus, you will use the sum rule. Okay, so basically you need to count the number of maximal matchings in this case, and you need to count the number of maximal matchings in this case. That's it, very easy. Now let's see the first one. Means this age 1, 2 is taken. Okay, this age 1, 2 I have taken in the maximal matching. If I've taken this 1, 2 in the maximal matching, then definitely 2, 3 I cannot take in the maximal matching. Yes or no? Okay, remember, if this age 1, 2, if I take it in the maximal matching, then definitely this 2, 3 is, this I cannot take in the maximal matching. Now, in this remaining graph, I need to create a maximal matching. Yes or no? So very simple point, that if I take this 1, 2 in the maximal matching, I cannot take 2, 3 because 1, 2 and 2, 3, they are adjacent edges. Now you can see that in this remaining graph, we need to find maximal matching. In this remaining graph, we need to make maximal matching. Okay, what is this remaining graph? This remaining graph is Pn minus 2. Okay, so very simple, that in this remaining graph, how many maximal matchings will be there? That is what we need to count. So in this remaining graph, this is Pn minus 2. How many maximal matchings will be there? That is Sn minus 2. Because what is Sn? This is the number of maximal matchings in Pn. So the number of maximal matchings in Pn minus 2, that will be Sn minus 2. I hope you understood this so far. Remember, we are considering those cases where this age 1, 2 has already been taken in the maximal matching, because there are only two cases possible. Either in the maximal matching you will take this age 1, 2, or you will not take this age 1, 2. So first we are considering those cases where AS12 has been taken in the maximal matching. If you take this 12 in the maximal matching, then 2 3 I cannot take. Now in the remaining graph, you need to make maximal matching. So you need to count the number of maximal matching in this remaining graph, and that is Sn minus 2. Now let's see those cases where this AS12 has not been taken in the maximal matching. Okay, remember, if you take this AS12 in the maximal matching, you will get Sn minus 2. But if you don't take this 12 in the maximal matching, then how many maximal matchings will be there? This is what we need to find. So if I don't take this 12 in the maximal matching, now total how many maximal matching I can create? Notice, if I don't take this 12 in the maximal matching, then I have to take this 2 3, because if I don't take 2 3 also, and then in this remaining graph if I create a maximal matching, then that will not be maximal, because I could have taken this 12. Do you agree with me? Very simple. We are counting the number of maximal matchings, those maximal matchings where, remember, it's very simple. We are counting those maximal matchings where this AS12 has not been taken. So this AS12 I'm not taking. Now, if I don't take this 2 3, then from this remaining graph, if I create some matching, then that will not be maximal, because I could have taken this 12, I could have added this 12 in that matching, and I could have gotten a bigger matching. Okay, so very simple point, that if I don't take this 2 3 also, then from the remaining graph, whatever matching I will get, that will not be maximal, because I could have added this 12. So I can say that if you don't take this 12, then definitely this 2 3 as you must take. Okay, I can say that from here, this is actually an implication, remember, means from here this implies that 2 3 I must take. Now remember, if I must take 2 3, then I cannot take 3 4. Now in this remaining graph, I need to make maximal matching. Okay, so this remaining graph, this is path graph on n minus 3 vertices. So remember, we are counting the number of maximal matchings which do not contain the AS12. So that basically will be the number of maximal matchings in this remaining graph. What is the number of maximal matchings in this remaining graph? That is Sn minus 3. Okay, that's it. I hope you understood. So finally, the recurrence relation we got, remember, this is the recurrence relation, Sn minus 2 plus Sn minus 3. And remember, this recurrence relation will work when n is greater than equal to 4. What is the reason? This recurrence relation will not work if you have n equal to 3 or 2, because if I put n equal to 3, think about it. If I put n equal to 3, then S3 will be equal to S1 plus S0. What is S0? That is the number of maximal matchings in P0. But we don't have P0. Every graph must have at least one vertex. We have path graph on one vertex, path graph on two vertices, but we don't have path graph on zero vertex. So very simple, that this recurrence relation will work for n greater than equal to 4. Okay, if I put n equal to 4, then S4 will be equal to S2 plus S1. We can count S1 manually, we can count S2 manually. Those will be the base cases. Okay, I hope you understood. So remember, very simple, that what is Sn? Sn is the number of maximal matchings. Number of maximal matchings in Pn. And the recurrence relation we already found, that this Sn will be equal to Sn minus 2 plus Sn minus 3 when n is greater than equal to 4. And what are the base conditions or base cases? What are the base cases? Let's see the base cases quickly. What will be S1? Tell me, what will be S1? See, S1 means path graph on one vertex. This is path graph on one vertex. So what will be S1? S1 is the number of maximal matchings in P1. So that only will be 1. This graph, path graph on one vertex, this does not have any edge. Yes or no? Because there is only one vertex, so there is no edge. If there is no edge, then what matching can you create? What maximal matching you can create? That will be empty set. Yes or no? Because matching means set of edges which are pairwise non-adjacent. And remember, empty set means you don't take any edge, then that is also a matching. And for this path graph on one vertex, that will be maximal matching because there is no edge. So what matching you can create? That will be empty set. Okay, so you can see that in this path graph on one vertex, how many maximal matchings will be there? S1 means the number of maximal matchings in P1, that will be 1, because what that will be? That will be empty set, or I can say phi. What is this phi? This phi is basically, remember, this phi is basically, this is a maximal matching. This is a maximal matching in path graph on one vertex. Okay, is this clear? Very simple. What about P2? P2 means path graph on two vertices. So in this P2, how many maximal matchings will be there? Means what is S2? S2 means the number of S2 means the number of maximal matchings in P2. So how many maximal matchings are there in this P2? There is only one edge that I have to take. So there is only one maximal matching. A1, A2, this edge I have to take. Okay, yes or no? So because there is only one edge in this P2, there is only one edge that I have to take. So I can say that the number of maximal matchings in P2, that will be 1. What about P3? P3 means path graph on three vertices. In this P3, how many matchings will be, how many maximal matchings will be there? What is S3? S3 means the number of maximal matchings in P3. So how many maximal matchings I can create? You can see there are two edges and they are adjacent. So either I can take A1, A2, either I can take this edge, or I can take A2, A3, this edge I can take. So I can say that S3 will be 2. The number of maximal matchings in P3, that is S3, that is 2. Okay. So these are the base cases. I hope you understood. So you can see that S1 is 1, S2 is 1, S3 is 2. Okay. So finally, I can say S1, 1, S2, 1, and S3, 2. So now we can find what is S4. S4 will be equal to S2 plus S1. You just have to apply this recurrence relation. What is S2? 1. S1, 1. So it will be 2. S4 will be equal to 2. What is S4? This is the number of maximal matchings in P4. And that will be 2. You can check it out yourself. You can see it here. This is P4, path graph on 4 vertices. And if you find how many maximal matchings are there, then you can see if I take this as 1, 2, then I cannot take this 2, 3, then I will take this 3, 4. So you can see 1, 2, 3, 4. You can see this is a maximal matching. If I don't take this 1, 2, then I must take 2, 3. If I take this 2, 3, then I cannot take this 1, 3. I cannot take this 1, 2. I cannot take this 3, 4. So I can say that this will be a maximal matching. So you can see the number of maximal matchings in P4, that is S4, that is equal to 2. Okay. You can easily find what will be S5. S5 will be equal to S3 plus S2. S3 plus S2, that will be 3. Okay. You can see what will be S6. That will be S4 plus S3. S4, that is 2. S3, that is 2. So that actually will be 4. What will be S7? You can find it easily. That will be S5 plus S4. S5 plus S4, that will be 5. Okay, and so on. I hope you understood. Now, did you notice one thing? This was our TIFR question. That in the path graph on 6 vertices, how many maximal matchings are there? This was our TIFR question. This was our TIFR 2022 question. Okay, and the answer will be 4. In the path graph on 6 vertices, the number of maximal matchings will be 4. Okay, so you can see the answer will be 4. I hope you understood. So we have solved this question using two methods. One method is manual, or I can say brute force. Using that also we got the answer 4. And another method is thinking recursively. Which method did you like the more? Tell me. Of course, thinking recursively, because you can solve any question. They can give you path graph, cycle graph, complete graph, any graph they can give you, and they can ask you the total number of maximal matchings or the number of independent sets, the number of maximal independent sets, and so on. They can ask you any question. Always think recursively, that's it. Very easily you can solve it. In this session so far, we have done multiple questions where we are thinking recursively to count the number of independent sets, to count the number of matchings in different questions. Okay, I hope you understood everything so far. So this is enough for this session. In the next session, we will continue our discussion of gate PYQs, TIFR PYQs. I hope you enjoyed this session. I hope you understood everything in this session. In this session, we have seen the recursive thinking to count the number of matchings, to count the number of independent sets, to count the number of vertex cover, and so on. Okay. So any counting related question related to matchings, independent set, vertex cover, and so on, you can just think recursively. This is what I told you in this session. I hope this session was helpful. I hope you loved this session. And from this session, based on this session, a lot of questions you can solve. In the next session, this GATE 2026 question we are going to solve where this path graph on 8 vertices, P8, path graph on 8 vertices is given to you, and the question is asking you to count the number of matchings. Remember, in the previous TIFR question, we have counted number of maximal matchings. In this GATE question, in this GATE 2026 question, we need to count the number of matchings. So there is a difference. In the TIFR previous question, we have count maximal matchings. In this GATE 2026 question, we need to count number of matchings. So of course, there will be some difference. Okay, but remember, the method is same. We will think recursively. I hope you understood. Okay, so in the next session, we are going to solve this question and some more questions where we will think recursively to count the number of matchings, to count the number of perfect matching, to count the number of maximal matching, to count the number of independent set, to count the number of maximal independent set, and so on. Okay, so I hope this session was helpful. Please share your feedback with me in the comments. You can write your feedback. Okay, thank you everyone. In the next session, we will continue our discussion. Thank you.